So again, all of this is just kind of what you should end up with is a map of the techniques that people use in mathematical physics. But let's start with separation of variables. And the idea is that this turns a partial differential equation, which is to say their partial derivatives, into an ordinary differential equation by assuming a product solution. And I'll write down the steps. In their most abstract way, and then we won't spend a lot of time talking about the heat equation, but the heat equation is a really good, nice first example of just seeing how this would work in practice. So let's say that I have a homogeneous partial differential equation. So L is some sort of differential operator. And in the back of your mind, you should think about differential operators as kind of if a function is like a vector, a differential operator is like a matrix. So you put in a function and it spits out a different function, except, it could have algebraic operations in it, but it could also have differential operators in it, like d by dx or d by dy or 2d by dy. So this is basically everything. Just about any linear differential equation, nonlinear differential equations are a different matter. But any linear differential equation can be expressed like this, and we'll do this for the heat equation, just to see how this would actually work. And now what I do is, oh crap, I'm going to get some things that have d by dx's, partial derivatives with respect to x. I'm going to get some partial derivatives with respect to y. I might get higher orders. And it's going to kind of look like a mess. So what I'm going to do is I'm going to assume a separable form. And I think this is the clearest notation, capital X of X and capital Y of Y, just because, so X is the function and the function X only depends on the variable X, and capital Y is a function. This function only depends on the variable Y. So an example of this might be like, alpha sine phi X e to the minus Y squared. So this is a separable solution where this is capital X only depends on X, and this is capital Y only depends on Y, right? So anybody think of an example of something that would not be separable? And they're out there. It turns out that there's just a huge class of problems you can solve without ever having to deal with them. So here's a non-separable equation, x to the y, or a non-separable form, and then sine of x times y would be one. So not everything has this form, but again, a huge swath of things do. And especially if you're thinking about gravitational or electromagnetic potentials, it makes a lot of sense. And you're going to be able to solve most physical scenarios, deal with most physical scenarios with a separable form. Okay, so why would I do this? This is just kind of rewriting my unknown function in terms of product of two functions. Well, so we'll call that step one. Step two is just go for it. So now just go for, have L acting on the product x times y. And if you have, an unknown function of r theta phi, you'd have three separable functions, a function of r, a function of theta, a function of phi. If you had, x, y, and z, you would have three separable functions. And you'll end up with terms that look like this. And this is just notation. So partial u with respect to x, we're going to define that to be u sub x. So this is partial derivative with respect to x. Again, this is standard PDE notation. I'm going to define that to be u sub y. And letting this happen, what you'll end up with terms that look like this. So now x, because it only, capital X only depends on lowercase x. So I'll only have terms that look like this, which is to say d big X, dx. And should I really be using the squiggly deltas for derivatives for this? Is this really a partial derivative now? Absolutely not. So now this is really dx dx, or to be honest, you know, if I wrote capital X prime, there's only one variable, so you guys would know exactly what this is. And likewise, capital Y, the only derivative that could happen is with respect to y, so that would be d capital Y with respect to y. Okay, so this is going to be kind of neat in the sense that you can see how this turns ordinary or partial differential equations into ordinary differential equations. The problem is everything's going to be smushed together. So what you need to do once you have this is algebraically separate them. If you can't do this, you're in trouble. So next thing we'll try to do, and without an actual example, I can't show you how this works. So that's what we'll do today. We'll algebraically separate. So ultimately, what you would get is things that only depend on, like, call it big F for some function. I don't know what the function is. There'll be functions of x and functions of x prime, and who knows what our differential operator is. So maybe you have second derivatives on one side, and then functions of some, if we can separate this, function of y prime, y double prime, y triple prime, all the way down to whatever order this partial differential equation happens to be. And then we'll make an argument that we'll make over and over and over. If these two functions are the same, no matter what choices of x and y you choose, so let's play this game. Like, I choose a value of x, and then I compute big F. Like, I find x, I find the derivative of this function at x, x is 4. And then you guys, without knowing my choice of x, you compute this side of the function by choosing your own personal values. Could be pi squared, could be, 1/50, it doesn't matter. But these are always equal. What must we know about these two functions, f and g? So no matter what x I choose and plug into the left-hand side, and no matter what y you choose and plug into the right-hand side, these two functions, f and g, are equal. What must be true about them? Exactly, right? So therefore they become constant. So if you can algebraically separate, and if it's okay to two reasonably big ifs, but if you can algebraically separate the result, and if you can assume a separable form, then all of a sudden this is the magic trick, is that this is an ODE and this is an ODE, and they equal a constant. Okay, so we'll do this basically for the rest of the class every time we have higher order diffie-q. So I'll leave this sit for 1 second. Any questions about that before we do an example of this program on the heat equation? Okay. So the heat equation, written in kind of goofball format, because we're going to have a time derivative, I'm going to say u of x and t is the temperature. And you can think about this as the temperature in like a long, thin rod. And we probably have some boundary conditions, like, we have u left as some constant and u right as some constant, or maybe we get even, crazier about it. So this is at L, and then we have some function of t, like we're turning on the oven, and then this is at 0. And then, we don't know what that is, but we'd like to find it. So long thin rod, which is why I'm just talking about x, whatever. And we want to know the function u of x and t, the temperature of the rod at all times. And we might be turning on the oven on one side or the other. So this is the heat equation. So K, all the material properties have to do with this thing K, the diffusivity. We have K U X X equals U T. So again, that's written in the kind of standard PDE notation. So the first question is, can you write this in this form? So, which is to say, what's the differential operator, big scripty L? Which has nothing to do with the other big scripty L, which is probably dominating your life in classical mechanics, which is
L would be del squared over del x squared on the left side. Oh, I see. I'm trying to get the whole thing equal to 0.
Yep. Yeah. So I think you have a divide where you might want to minus. So let me start by rewriting this in the more traditional way, I think. We're probably used to seeing. And then again, that's some unknown function of x and t. So this is a pretty big step, honestly, is where you stop thinking about d by dx always acting on a function like df dx, dt dx, whatever. And you start thinking about d by dx or d by dt or higher order derivatives as kind of like matrices. They're things that act on functions. And as such, you can move them around. And they exist outside of acting on a function in the same way that a matrix does. So what is it that the whole thing is acting on this unknown function u to give me 0?
It's the second partial derivative with respect to x minus the partial with respect to t.
Okay, so the way that you would describe this is I have a differential operator, which is some constant, has to do with material properties, second derivative with respect to x, first derivative with respect to t. So that's my differential operator. Kind of notation, but kind of useful. Okay, so now I want to separate variables. And you might be able to do that all in, maybe like one giant step, because this is a pretty nice equation. This is much nicer than, for instance, the the Laplacian or Poissons equation in spherical polar coordinates or something like that. So I'm going to be uncreative, call this capital X of X. And I'm going to call this capital T of T. So essentially the idea is that the spatial component and time component are separable. And especially space and time, that's kind of that's a bigger question than the X component and the Y component, for instance. So then I just plug this form into this. Differential operator LU equals 0 would be K, and then two X derivatives. X derivatives only act on X, so X double prime T, that's still there by the product rule. And then minus d by dt has nothing to do with X, T, and we can, again, just call this T prime because the only thing that T has in it is time, the time variable. So it's unambiguous. Like if you say the derivative of the function T, it's got to be with respect to time. People okay with that? Okay, now I want to algebraically separate. So it's going to be kind of weird because you're like, I feel like you're undoing the thing that you just did. And you're right. So I'll just solve this to put all the X stuff on one side, and I'll solve this to put all the T stuff on the other side. And I end up with X double prime over X times K is equal to T prime over T. Okay, so I'll say right at this point is like if it felt like you undid what you just did in question 1, I 100% agree. Just the idea of writing stuff in terms of differential operators, I want you guys to see it so you understand it if you come across it. For their entire PDE books where this is never done. So honestly, like, could have just taken the heat equation directly and done this. Okay, any questions about getting this? Okay, here's the magic step. If the left-hand side of this is equal to the right-hand side of this, no matter what X I choose, where along the bar, and what time you choose, they're always equal for any combination at all of X and T. Obviously, this needs to be equal to a constant. And what you'll see is that because people have been solving these for so long is that they know a really kind of elegant form of the constant. They'll say like it equals a constant. The constant is L times L plus 1. And you're like, why does it equal that constant? That's just a choice that's been, proven to be useful in hindsight. But anyway, we'll just say constant, and I'll call it alpha. How about that? So something that seems reasonable. Okay, so this is the part where I have two different ordinary differential equations. So what this becomes is two different ODEs. One is T prime over T is equal to alpha, or T prime equals alpha T. What's the thing whose derivative equals the function itself, but with a constant pulled out?
It's the exponent, right?
Yeah, so this is some constant e to the alpha t equals t of t. And then we have, second equation. It's a little bit tougher, but that's kappa x double prime is equal to alpha x. What's the function that satisfies two derivatives is equal to the thing itself, up to some constant? And I think there are 3 valid answers, I think. So the question is, which one do you think is the most reasonable?
I would say probably usually it'll be like a sum of sines and cosines, or a
Yep.
complex exponential, right?
Yeah, so sines and cosines or exponentials. What do you think would be the most reasonable thing to have, remembering that we're talking about the distribution of temperature in between here and here? So it'd be kind of sensible to think like the temperature might go like this or something. Seems a bit funky, right? So it's probably going to be just physical argument. It's probably going to be the exponential solution. Now, if this was minus and this is minus, so for instance, if alpha is less than 0, you would get a falling exponential, which kind of makes sense to me. And you don't have to worry about complex. So this is probably going to be also some exponential, call it capital D. And then really gross, but alpha over k x. Okay. And then the particular nature of A and D will be determined by the boundary conditions, which we haven't specified. And if it were sines and cosines, those, if you gave me, for instance, u of x at 0 is some function of x, yeah, I would absolutely have to make those into a Fourier series. So I'd have to choose a collection of sines and cosines to match onto that. Or x of x is equal to e to the minus I, call it dn I n x. So essentially Fourier series, or a single exponential if you're really lucky. Okay, so that's the whole program. And we won't do an actual boundary value problem. At this point you can say like, I bet I could do that because, had a fair amount of Fourier series practice. Okay, so if there are no questions about that, the next step is that we're going to try this, but for an electrostatics problem in spherical polar coordinates, just to see how this would work. And this will be sort of a warm up. On your next homework, you'll have the entire Laplace equation in full spherical polar. So no azimuthal symmetry. Which means I feel comfortable kind of skipping some steps. So that was the easy one. So it was, what is it? Green circle, blue square, black diamond. Is that how it goes? That was the green square. And just as a reminder, this is what we want to do. So del squared V equals 0, where V is the electrostatic potential. Or electric potential. And the nice thing about this is that so this is the full physical equation, so called Poissons equation. Oops, put that down here. So it's essentially Poisson's equation in the region where there's no charge. There's a minus sign there. And the electrostatic potential or electric potential satisfies del V equals E. Right. So conservative force makes conservative field. Therefore, there's a scalar function whose gradient is equal to the vector field, conservative vector field. So the nice thing about this is it's a scalar that we're trying to find, v. The bad thing about this is that we've traded our first order differential equation for a second order differential equation. Okay, so if we have azimuthal symmetry, what that means is if I look down the z-axis at whatever this thing is, it looks the same. So the charge distribution that ultimately causes the potential function and electric field can be a function of r and theta ultimately. And therefore v is only a function of r and theta. But because we're going to be solving Laplace's equation, we're looking in this region where there is no charge. So that's kind of the physics background of what we're about to do. Questions about that? Okay, so this part we go a little bit fast. We know that our solution is going to look like this. And what I will do is I will look up the Laplacian. Should have capital L in spherical polar coordinates. And what I get is that del squared v is equal to quite a lot. Okay, so this is d by dr. And this is the v sub r, that's the usual PDE notation. V is a scalar function. So it's not the rth component, it's the partial derivative of v with respect to r. Likewise, that would be the partial derivative of v with respect to theta. And this is the whole thing. It's a squared. And because we're saying we have azimuthal symmetry of the charge distribution and therefore the potential that it creates, is that we can just take this whole last term. So this would be two partial derivatives with respect to phi, but we've got no phi. So this whole term goes to 0. So the azimuthally symmetric Laplacian is just this stuff, which I'm not going to bother rewriting. Okay, so this is going to be our program. We've written our differential operator, so that's nice. That's part one. Part two is what should I do with v? So I got to make an assumption that will let me solve this nasty mess. So I'm going to assume a particular form for capital V. Namely that v of r and theta is equal to a separable form. So capital R of r, and then capital theta of theta. I'm happy to call it big T of theta if you guys don't like the capital theta. The good news is the second you assume a separable solution, you can just stop writing the dependent variables, the lowercase r's and the lowercase thetas, because everything will just become prime. Does that like reasonably straightforward enough notation? Okay. So we assume a separable solution. I'm just going to say calculus. So here, for instance, in this first term, I'm going to have capital R times capital theta. So this will be an R prime, but then I have to take d by dr of r squared times the r prime. So I'm going to get some extra terms. Likewise, this will just be capital R times a theta prime. So we're taking derivative with respect to theta. Then I multiply by sine and then take another derivative with respect to theta. So in the back of your head, you should kind of know where some of these terms are going to come from. So I am going to write one intermediate step. I think would probably make everything easy. I have so dr r squared r prime. So before things get a little bit kooky, this should at least make complete sense. Okay, so what I'm able to do is see all these matched r squareds down there. Since it's equal to 0, I just got rid of those. And then here I have partial v with respect to r and partial v with respect to theta, which, because we have a separable solution, just becomes r prime and theta prime. Okay, people happy with that? Because I ran out of whiteboard space. Great. So now I have this, and my goal is to separate them. So to separate them, it turns out this is pretty easy. I just can divide everything on the last thing that I just erased. So take my word for it, but you guys will basically replicate this. So we want to algebraically separate. So we did the calculus, now we want to do the algebra. And I'll give you a hint, it was, because I don't think this is like super obvious, we divided by, or multiplied by 1 over v, which is 1 over r theta. So we really should say multiply by both sides. And we end up with this. Okay, this is a big old plus. And what I could have done is I could have put this left term on one side and kept the right term on the other side. But I think it's clear enough that if you look at this, we have nothing but r's, right? Big R only depends on little r. We only have derivatives with respect to r. We only have little r's. We only have big r's. So this is what we'll call the radial equation. And we'll call it double star. And this is the so-called axial equation. It only depends on thetas. And what must be true, so again, the game is I pick any r and I dump it into the radial equation, you pick any theta and dump it into the axial equation, and somehow magically they sum to 0. So same argument, just rephrased a little bit. What must be true about the radial and the axial equations? Throwing one tiny little curveball at you. So in this case with this phrasing, it's not true that double star equals triple star. It's equal to the opposite. And if that's true for any value of r and theta, so for all r, and r can be anything in between 0, the entire positive real line, and theta can be anything in between 0 and pi over 2, then what must be true is they must be equal to constants. So the axial equation needs to be constant. The radial equation needs to be a constant. So we have two ODEs. One ordinary differential equation. This is just, and because now it's all by itself, I can call it d by dr with straight up and down d's, not the partial d's. And for now, I'll call this kappa. This is one of those things with like the weird kind of hindsight rephrasing of the constant. We have the second ODE, d by d theta. And again, not a partial derivative now. Okay. So just because people have solved this a lot, and you can kind of see where this might come from, is we have one derivative here and another derivative here. So after we do a little bit of kind of fussing with this, we're going to ultimately end up with two second order differential equations. So it turns out to just make life a little bit easier to call the constant L times L plus 1. That's just a useful way of choosing the constant. Okay, so people okay with that so far? Okay, so this is a lot of the formal work. Now what people do is generally just kind of stop and talk about solving these things separately. Sometimes they have different names, like Legendre's equation will come out of this, for instance, or Bessel's function. So this is the separation of variables part. Now what we're going to do is we're going to pick apart each one of these separately and discuss their individual forms of the solutions, and then learn how to paste them all together to solve spherical polar coordinate problems.